Okay, so now for chapter 2.3, we're going to be doing complex numbers. So let's start with the imaginary unit I. So before, when we were doing square roots, we said we could not take the square root of negative numbers. We couldn't have a negative in the radicand. So for example, if we had x squared equals -1, and we wanted to solve that for x, what we would do is we would take the square root of both sides, and we would get x equals plus or minus the square root of -1. So originally we said we cannot have that, but now we're actually going to be able to have that. A square root of a negative is going to imply we have imaginary numbers. So the imaginary unit I is going to be defined as the square root of -1. So if I equals the square root of -1, that means I squared equals -1. So that means for x squared equals -1, the solutions would be x equals plus or minus I. So it looks pretty weird if you haven't seen it before, but that's the imaginary unit. Okay, so getting down into complex numbers and imaginary numbers now. So the set of all numbers in this form, a plus bi. So a and b are just real numbers here. And I is the imaginary unit, so a plus bi. This is the set of all complex numbers. So if we have this b value, if b value equals 0, then that whole second term actually cancels and we're just left with a. So if b equals 0, that means it is just a real number that we've always been working with. If b is not equal to 0, then the number is an imaginary number. And if it is just bi, so just a number times I, it's called a purely imaginary number. So the a over here is called the real part, and the b is called the imaginary part. Okay, so the set of real numbers belongs to the complex numbers, and the set of imaginary numbers belongs to the complex numbers as well. So for some examples here, let's say we have -4 plus 6i. So it looks pretty weird when you're looking at it like this. This is as simplified as it can get. This is just one number. This is one complex imaginary number. Technically, these are two-dimensional numbers. We could plot them on XY axes, but we won't get into that right now. So the real part here would be -4, and the imaginary part would be 6. Okay, so another example would be 2i. So this one would be purely imaginary because there is no real part. And lastly, something like 3. So this is just a real number, right? 3. We could write it as 3 plus 0i. So this is just showing that real numbers belong to the complex numbers, where the imaginary part is equal to 0. Okay, so this pretty much just extends our definition of numbers with the new set of complex numbers here. So a complex number is simplified if it's in the form a plus bi, and we call that standard form. So we're going to be doing several operations with these. We're going to be adding, subtracting, multiplying, and dividing. Adding and subtracting is hopefully relatively easy. Multiplying and dividing will be a little bit more difficult. So when we're adding and subtracting complex numbers, so something like a plus bi plus c plus di, all we have to do is add or subtract the real parts together. So it'd be like a plus c. And then add or subtract the imaginary parts together, so like b plus d. So when we add those together, we add the real parts and add the imaginary parts and multiply the imaginary unit I on that portion. And then same thing if we are subtracting, we're just going to be subtracting those instead. Okay, so let's do some examples here. So perform the indicated operation and write the answer in standard form. So standard form a plus bi. So we have 5 minus 11i plus 7 plus 4i. So I'll go through these ones kind of quickly because it's kind of just like combining like terms. So we have our real parts right here. So we're adding, so we're going to add those together. 5 plus 7 is 12. And then we have our imaginary parts here. Negative 11 plus 4 is negative 7. So that's negative 7i. So you combine those just like we combined it if it was like a variable x, essentially. Okay, and next one we have negative 5 plus I minus 11 minus 6i. So what I'm going to do here is actually just distribute first. So I'm going to leave that first complex number alone, and I'm going to distribute that negative. And I'm only doing that just to help us combine like terms easier. So we have negative 5 minus 11 is going to be negative 16. And then I plus 6i, that's 1 plus 6, so plus 7i. So notice that these are in a plus bi form for our answer. And the last one here, 7 minus 10 minus I. So I'm going to distribute that negative again into that second complex number. 7 minus 10 plus I. So 7 minus 10, we get negative 3. That's negative 3 plus I. Okay, so even though these are called imaginary numbers, they still exist. They're not imaginary at all. They still exist, so don't let the name throw you off. Okay, so that's adding and subtracting. Hopefully that was pretty self-explanatory, combining like terms essentially. When we're multiplying, this is also going to be hopefully self-explanatory. We're going to be using the same rules as when we multiplied like polynomials. We're going to have to remember how to distribute. And since complex numbers can be thought of as a binomial because they have a real part and an imaginary part, we'll be distributing as foiling. And the important thing here is when this happens, we're going to be multiplying an I times an I, most likely at some point. We have to simplify that, knowing that I squared equals negative 1. So anytime you get an I squared, you have to replace it with a negative 1. And the reason is because we're going to want these answers in standard form. Okay, so let's multiply these and write in standard form. So we have 4i times 3 plus 5i. So we have to distribute. So we're going to distribute this 4i into that second complex number. We're going to get 12i plus 4 times 5 is 20. And I times I is I squared. Okay, now we need to use the fact that I squared, this equals negative 1. So it's going to be 12i plus 20 times negative 1. And this is going to give us 12i minus 20. So I'm just going to write this in standard form, writing the real part first. That's negative 20 plus 12i. Okay, next one. We have 7 minus 3i times negative 2 minus 5i. So we're going to have to distribute by foiling both of these in here. So distributing the 7 first, we're going to get 7 times negative 2 is negative 14. 7 times negative 5i is negative 35i. Now distributing the negative 3i. Negative 3i times negative 2 is positive 6i. And negative 3i times negative 5i is positive 15i squared. So I times the I, we get I squared. Combined like terms in the middle here, we have these two I terms. We have negative 14, negative 35i plus 6i gives us negative 29i plus 15. So instead of I squared, we're going to write the I squared as negative 1. So that's negative 14 minus 29i minus 15. And we are going to combine like terms. Negative 14 minus 15, we get negative 29 minus 29i. So that's our answer in standard form. Okay, and then for the next one here, do one more before we get into dividing. So we have 2 plus I times 10 minus 9i. So we are foiling once again and multiplying the 2 into the other complex number. Distributing the 2, we get 20 minus 18i. And now distributing the I, we get plus 10i minus 9i squared. Okay, so now for simplifying, we need to combine like terms in the middle. That gives us 20 minus 8i, negative 18 plus 10. And then replacing the I squared with a negative 1. This is going to be 20 minus 8i plus 9. Combine like terms, that's 29 minus 8i. Okay, so that is our answer in standard form for this one. So imaginary numbers, even though you may not see them all the time, they get used all the time in applied mathematics. They're always used in solving, not always, but mostly used in solving differential equations, which I won't get into, but that's a big topic in electrical engineering. So it has these very real, useful applications. Okay, so now for dividing complex numbers. It's the most complicated operation for these. So to do this, to divide complex numbers, what we have to do is multiply the numerator and denominator by the complex conjugate from the denominator. So if you remember what a conjugate is going to be the same two terms, but one is addition and the other is subtraction. So the complex conjugate of a plus bi is a minus bi, and vice versa. So we'll kind of see why this is useful right here. When we multiply them together, a plus bi times a minus bi, what we end up getting is a squared plus b squared. So we get a squared plus b squared. So if you remember when we multiplied conjugates together before, I'm going to erase this in a second. When we multiplied conjugates before without complex conjugates, without an I, the shortcut was a squared minus b squared, right? You could FOIL that out, you'd get the same thing. So the reason, or if you recognize the difference here is addition and subtraction, is because of the I squared equals negative 1, it's going to end up negating that term. So let's see what happens here. So the reason why this is useful is because you are completely getting rid of the imaginary part for this. A squared plus b squared is just going to end up simplifying to just a number, a real number. So let's FOIL this out to see why this is the case. So a plus bi times a minus bi. If we FOIL this, distribute the a, we get a squared minus abi. Distribute the bi, we get plus abi. And then distributing the last part here, we get negative b squared times I squared. So these two middle terms cancel because they're the same with opposite signs. And we're left with a squared minus b squared times I squared. So hopefully you can kind of see what's happening here. We get a squared minus b squared times negative 1 because I replaced the I squared with a negative 1. And this is just going to negate that second term. So we get a squared plus b squared. So you don't have to do it the long way. You can just use the shortcut way and say it's going to be the real part squared plus the imaginary part squared. Okay, so let's divide these, do several examples of these. So we're going to divide and write the answer in standard form. So we have 3i divided by 4 plus i. So we have to multiply by the conjugate of the denominator. the conjugate of 4 plus I is 4 minus I. So we're going to multiply the numerator and denominator by 4 minus I. And what that is going to do is going to get rid of any imaginary part in the denominator, and we're just going to have a real number down there. So I'm just going to rewrite this so it's 3I times 4 minus I divided by 4 plus I times 4 minus I. So let's do that let's do this denominator over here on the side. Let's do 4 plus I times 4 minus I. So it's going to be the real part squared plus the imaginary part squared. So that's going to be 16 plus 1, so 17. So the real part, or the imaginary part rather, is 4. The real part, or the imaginary part, is 1 because nothing is written there. So that's going to be 4 squared plus 1 squared, 17. So that whole entire denominator is just going to be equal to 17. So now we can distribute in the numerator. 3I times 4 is 12I. 3I times negative I is negative 3I squared. So simplifying that numerator, because we have an I squared up there, we can rewrite that as negative 1. So it's going to be 12I minus 3 times negative 1 over 17, which is going to be 12I plus 3 over 17. And writing this in standard form, I'm going to flip the order, and I'm going to give each part in the numerator its own denominator and make it 3 over 17 plus 12 over 17 times the I. So the reason I did that is because now we got it in standard form, A plus BI form. Okay, so let's do 2 more here. We have 7 plus 4I divided by 2 minus 5I. So we have to multiply the numerator and denominator by the conjugate of the denominator, which is 2 plus 5I. So all we have to do is change it negative to positive, subtraction to addition. So we can do this because we're technically not changing anything, right? We're multiplying by the same thing in the numerator and denominator. So rewriting this, I'm going to rewrite it as 7, just to make it look a little better. So we get that, and I'm going to multiply that denominator on the side again. So just multiplying this over here, it's going to be 2 minus 5I times 2 plus 5I. So it's going to be the real part squared plus the imaginary part squared. 4 plus 25, we get 29. So that whole nasty denominator is just going to be 29. And for the numerator, we have to FOIL. So 7 times, so in the numerator, distributing the 7 first, 7 times 2 is 14. 7 times 5I is plus 35I. Now distribute the 4I, so we get plus 8I, and then plus 20I squared. Okay, so that whole thing is in the numerator, so we obviously have to simplify that. Combine those like terms in the middle, 35I plus 8I, we get 43I. So we get 14 plus 43I plus 20. Instead of I squared, we write a negative 1. And we get 14 plus 43I minus 20 over 29. And this gives us 14 minus 20 is negative 6 plus 43I over 29. And for the final answer, I'm just going to split it up that fraction, give each term its own denominator. So it's negative 6 over 29 plus 43 over 29 times the I. Okay, so Now it's in standard form. That is our final answer. Let's do one more here. We have 2 minus 7i divided by 9 plus 3i. So multiplying the numerator and denominator by the conjugate of the denominator, the conjugate of 9 plus 3i is 9 minus 3i. And just rewriting this so it looks a little cleaner, we end up rewriting it like this. So same thing, just rewritten. And let's multiply that denominator on the side just so it doesn't get too cluttered. So multiplying complex conjugates, the real part squared plus the second part squared. So that was the 9 squared plus the 3 squared. So notice how I just look at like the first one that's written, because you only need one of them to figure out the a and b that you're using to square and add. So 9 squared is 81. 81 plus 9, we get 90. So that whole denominator is 90. So it's going to be something over 90. And now we have to FOIL that numerator. So let's take this 3 and distribute the 2 into the second one. So it's going to be 18 minus 6i. And now let's distribute the negative 7i. That'll give us negative 63i plus 21i squared. And now same thing as last time, we just have to combine like terms and simplify here. So negative 6i minus 63i, that'll give us negative 69i. And then replace the i squared with a negative 1. And we have to simplify. We get 18 minus 69i minus 21 over 90. 18 minus 21 gives us negative 3 minus 69i over 90. And what we can do is split this up. Negative 3 over 90 simplifies to negative 1 over 30. So that's 3 over 90 simplifies to 1 over 30. And 69 over 90 simplifies to 23 over 30. So I just simplified the fraction. Well, I gave each term in the numerator its own denominator, and then simplified the fractions in one step. Okay, so that's adding, subtracting, multiplying, and dividing complex numbers. So for the last couple things here, we have roots of negative numbers. So for any positive real number b, the square root of the negative number, negative b, is going to be the square root of negative b equals I times the square root of b. So this is because if we have the square root of negative b, thanks to exponent rules, because the square root is an exponent of 1/2, we can rewrite this as, because it's essentially negative 1 times b, we can rewrite it as the square root of negative 1 times the square root of b. The square root of negative 1, that's the definition for the imaginary unit, so that's I. So it's I times the square root of b. But you can just skip to that last part of it. So for example, if we have the square root of negative 25, we know that this is going to be equal to I times the square root of positive 25, which the square root of 25 is 5. So we write this as 5i. So notice that I put the real portion first, the real part first. Okay, or we can have something like square root of negative 16. We know that's going to be I times the square root of positive 16. Square root of 16 is 4, so that equals 4i. Okay, so let's use that concept and a concept that we already know to do these problems here. So let's perform these indicated operations and write the result in standard form. So we have the square root of negative 18 minus the square root of negative 8. So first, let's do that property that we just learned. That's going to be I times the square root of 18 minus I times the square root of 8. Okay, so if you remember this now, we have to get like radicands in order to combine them. So we can rewrite 18 as 9 times 2. We can rewrite 8 as 4 times 2. So now it's going to be the square root of 9 is 3. So this is 3i radical 2 minus the square root of 4 is 2. So 2i radical 2. So now we accomplished our goal of getting like radicands of radical 2. So now our coefficients, what we're adding, is going to be 3i minus 2i. So 3i, or 3 minus 2 is 1. So we're left with 1i radical 2, which obviously we don't need to write the 1. So that would be our answer. Okay, so let's do another one. Same concept. We have to get like radicands. So 3 times the square root of negative 20 plus 2 square root negative 45. So first, let's take care of that negative under there by writing it as an I out front. So 3i radical 20 plus 2i radical 45. So now we need to get like radicands. We need to think of two factors for each of these radicands separately, where one of them is a perfect square. So for 20, we can rewrite that as 4 times 5 because 4 is a perfect square. For 45, we can write that as 9 times 5 because 9 is a perfect square. And we have the square root of 4 is 2. So this is going to be 3i times 2 radical 5 plus 2i times square root of 9 is 3. So 3 times radical 5. Now we can simplify because we're just multiplying. So it's going to be 3 times 2 is going to be 6i radical 5 plus 2 times 3 plus 6i radical 5. So 6 plus 6, we get 12i times radical 5. Okay, so let's do 2 more here. We have negative 1 plus radical negative 5 all squared. It's a little bit different, but we should know how to do this still. So what I'm going to do here is I'm going to rewrite this as negative 1 plus I radical 5 all squared. So I just changed the square root of negative 5 to I times the square root of 5 using that same property. And now let's write this as negative 1 plus I radical 5 times negative 1 plus I radical 5. So instead of writing it using the squared, you can write it like that because there's 2 of them being multiplied together. And now let's FOIL this out. So first, let's distribute the negative 1. So distributing the negative 1, we get positive 1 minus I radical 5. And now let's distribute the I radical 5. We get negative I radical 5 plus I squared radical 5 times radical 5 is equal to just 5, right? So I squared times 5. So I'm going to write this like that for now. So I know I didn't show every step with foiling it out, but hopefully we know how to FOIL. And let's simplify this. So we have these 2 middle terms are exactly the same. So it's negative 1 minus 1 essentially. So we get minus 2 of them. So negative 2i radical 5 plus, I'm going to rewrite that I squared as a negative 1. So it's going to be minus 5. And I'm going to combine like terms here. 1 minus 5 is negative 4. So negative 4 minus 2i radical 5 would be our final answer because that is in standard form now. So kind of messy, but still pretty doable. And now for the last one here for D, we have negative 25 plus the square root of negative 50 all over 15. So once again, let's take care of that negative under the square root and say that's going to be negative 25 plus I times the square root of positive 50 over 15. And for the square root of 50, I'm going to rewrite the square root of 50. I'm going to rewrite 50 as 25 times 2. So I'm just trying to simplify that 50 because 25 times 2 equals 50. 25 is a perfect square, so it simplifies. So we get negative 25 plus radical 25 is 5, so 5i square root of 2 over 15. And kind of the second last step here, let's split up this fraction. Just always keep in mind your goal is to get this in a plus bi form. So I'm going to give that denominator to each part in the numerator. So we end up getting this. And now lastly, let's just simplify it. So negative 25 over 15 simplifies to negative 5/3. For this part over here, we can simplify the 5 divided by 15 equals 1 over 3. So that's going to be 1 over 3. So that's going to be plus 1 over 3 times radical 2, which is radical 2 over 3, times that imaginary unit I, and there is our final answer. Okay, so all I did there is kind of rearrange it a little bit and simplify. Okay, so that's in standard form, so we're good, and that is it for complex numbers.